when some kind of driving is here, and what happens for a two-terminal junction. What is that and what these mean? So I would talk in the next or so. So these are my collaborators. I would like to thank both of them. They are from Tel Aviv University. So what I am going to talk about is basically when you have a two-terminal junction. Say for example, you have some system which is connected to two reservoirs via two leads, and you are imposing some kind of external parameters, like in my case it's some kind of time dependent spin orbit coupling, and what happens to the different physical properties, say for example thermoelectricity, magnetism and short noise. So these are the paper where you can find the details. So this is the short noise thing, is some kind of a ongoing project. So I would mainly talk about the thermoelectric part because time is limited. So this is the outline of my talk. So first I like to give some overview on the two main aspects, like spin orbit coupling and thermoelectricity. Then I would talk. Then I would like to show you our results, and in case of thermoelectricity and the short noise case, if time permits. So basically, we all know about spin orbit coupling. It's basically the coupling between spin and orbital angular momentum. So when you start from the Dirac equation, and want to have some semi-classical limit of the Hamiltonian, you go through that by either by Paul-Davidson transformation or some other transformation, and finally you have many terms. I have not written here. There might be some Darwin term and some kinetic term, some potential term, and this is the most important part. This is basically the spin orbit coupling term. And in case of condensed matter systems, say for example the 2D electron gas, you can have some intrinsic spin orbit coupling, say for example some Rashba spin orbit coupling, and one can identify that if your electric field, which is the gradient of this potential, you can jump to this formula by using some z direction electric field. So basically the takeaway message from this slide is that when you consider your E cross P as some effective magnetic field, then it exactly looks like some Zeeman term, but the point is it is different from Zeeman term because it obeys the time reversal symmetry, but in case of the real magnetic field, it actually breaks that. So this is the takeaway message. And also I like to give some overview on the thermoelectric part. So we all know what is thermoelectricity from our school days, like when you create some junctions between two metallic wires, say for example, and if you keep these two junctions at two different temperatures, you can have some current flow in the circuit. So this is called the famous Seebeck effect, and if you want to have some similar effect in the two-terminal junction, when you have some mesoscopic or nanoscale system and you connect this system to two reservoirs with difference in temperature and difference in chemical potential, then in your system two different kind of currents actually comes into play. So these two currents are the particle current and the energy current. So this JE is the energy current, and this is the heat current which is connected to the energy current by this relation. So when you try to write these currents in terms of the driving forces, in our case the driving force is the difference in temperature and difference in chemical potential. So if you want to write these currents in terms of these driving forces up to linear order, which we call the linear response theory. So we have some matrix, and this matrix is called the Onsager matrix, and these elements are Onsager matrix elements, and these elements are related to the thermoelectric conductivities via these relations. So I would like to use these things when I discuss my results. So the important thing or the takeaway message from this slide is we have these relations for the electrical conductivity, the thermal conductivity and the Seebeck coefficient. And what happens with all of these, if you you can define some figure of merit with these conductivities, and this figure of merit determines whether your system is a very good thermoelectric material or not, if when you can increase this value of the figure of merit. So let me also discuss a few things about the two-terminal junction. So when you apply some spin-orbit coupling to a two-terminal junction, you always want to have some spin polarization at the output. So the question is whether one can have the spin polarization in a two-terminal junction with some static spin-orbit coupling. So the answer is no. Why it is no? Because when you apply this spin orbit coupling to these links here, you want to have the conductance. This is the famous Landau-Brütiger formula, and for the conductance you need to know the transmission amplitudes. So these transmission amplitudes are affected by the spin orbit coupling for sure. So these are the phases that affects the transmission amplitude. These phases are called the Arhanov-Kasher phases, and if you do so and you want to have this TT dagger which is needed for the transmission, for conductance, so this simply boils down to T0 square. So this T0 is basically the tunneling amplitude without spin orbit coupling. So finally what we don't have any visible effects on the conductance. So what is the way out, and why this is happening? So this is happening because in two-terminal junction, the spin orbit coupling actually preserves time reversal symmetry, and because of that we don't have the spin polarization in the system. So it can't polarize the spin because one spin goes this way, another spin goes this way, and they cancel each other. So we finally don't have any spin polarization at the output. So what is the way out? So way out, one can, so why we are looking for way out? Because we don't have the spin polarization in presence of static spin orbit coupling. So we want to have some time reversal symmetry breaking in the system. So how to do that? One thing immediately comes to our mind is to use some magnetic field. Because we all know that magnetic field breaks the time reversal symmetry, but we don't want to have a magnetic field on top of the spin orbit coupling. Another thing is to use a third terminal. And if you add a third terminal and want to measure the current between any of these any two of them, then you can have some time reversal symmetry breaking. But we want to have the effect in two terminal junction. So what is the way out? We are using some time dependent spin orbit coupling by using a time dependent electric field in the system, and doing that we let us see what happens. So first thing that if we use some time dependent spin orbit coupling, then it breaks the time reversal symmetry, and it is exactly what we needed. So this is our system. We use a quantum dot which is connected to two reservoirs at two different temperatures, and we use some z direction electric field which acts on these weak links. And DL and DR, these are very important factors, because these are the distance between this quantum dot with the reservoirs, and this actually determines whether your system is a mirror symmetric system or you can induce some asymmetry in the system. So this is our system and the corresponding Hamiltonian. So this is the Hamiltonian of the dot, this is tunneling Hamiltonian, and these are for leads. And the tunneling Hamiltonian, as I have mentioned previously, the tunneling amplitudes are modified by this phase factor, which is the Arhanov-Kasher phase. So now this phase factor carries some time dependence. So let us move to the next slide. So this is exactly the system, and with some explanation, let us keep that. So what we are interested in? We are interested in the thermoelectric coefficients, and the thermoelectric coefficients are related to the Onsager matrix elements. So we need to write the currents in terms of the linear response regime, so that we can have the matrix that I had shown previously. So to do that, we have this particle current, which is the time derivative of the number operator at that lead, and we also have some energy currents. Here we have a lot, but when you take some time averaged case, then you only have single energy current that survives, that I would talk about in the next slide. But here let us focus on the particle current case. So this is the averaged particle current averaged over a single period. So so look at the expressions. So we have two different terms. So in the first term, this FL and FR are the Fermi functions of the two reservoirs. Then if you ask me what happens when you don't have any biasing. So if you don't have biasing, means your two sides Fermi function, that is there is no temperature difference and no chemical potential difference. So this term goes away. Now look at this term. This is completely the effect of spin orbit coupling. You can see it is of the order of omega square. So you can see that it has dr square and dl square, and FR is even FR equal to FL, this term survives. So one can conclude that in case of a mirror symmetric system, the particle current is 0 without biasing. But if you create some kind of a mirror asymmetry in the system, your DL is not equal to DR, and you can have some kind of particle current which is coming totally because of the spin orbit coupling and the time dependence of it. Okay. So this is the average energy current. So these two terms you can identify with the particle current case. Without the difference is, here we have a factor of omega, that is the energy, which is quite obvious. So the same explanation goes with this. For the two cases I have mentioned, that is FL is equal to FR and DL is equal to DR. But here we have some extra term. So this PL is the power that the source of the spin orbit coupling actually generates and gives towards the system. So this power, you can see that whether your FL is equal to FR or DL equal to DR, this power survives. So this is the interesting result that we are getting, that even if your particle current is 0 in the situation when your FR is equal to FL and DR is equal to DL, your energy current still survives. So this is the case. Now, as I have mentioned this previously, so let us see the Seebeck and thermal conductance. These are written in terms of the integrals, these integrals. So you need to do these integrations. So you can do it by numerically or some approximation. So we did it numerically in one case, and in the other case we use the low temperature approximation. So you can see that here the thin plot is without spin orbit coupling and the thick plot is with spin orbit coupling. This is the numerical result. So you can see that after a certain region, your spin orbit coupling takes the charge, and it's much higher than the without spin orbit coupling case. This is the Seebeck coefficient that we are looking for, because you should have higher values of Seebeck coefficient in your system to have a better thermoelectricity. And this is the thermal conductance, and you can see that it should be lower because it's in the denominator in the expression of the figure of merit. So you can see that we are finding a very small region where it dominates. I mean, the without spin orbit coupling dominates the with spin orbit coupling case. So this is basically the result. Let me now discuss the efficiencies. So say for example, if you have this system and you can create one of the reservoirs as hotter and another one is colder, then you can have a heat engine kind of a scenario. So if this is the situation, then you can calculate the efficiency for the heat engine. So the efficiency is what you get by what you pay. So we are getting some electric power in the system and we have the heat current. So this is the definition of the heat engine. And we all know that it is maximum for the Carnot case. Now we are looking for whether adding this time dependent spin orbit coupling improves this situation. So this is the goal of this section. And for the heat pump, which is sometimes the famous example is the refrigerator. So it's basically the reverse definition is applicable here. So let me skip these two slides. And so this is the final expression for the efficiencies. This is for the heat engine case, this is for the heat pump case, and this TS dot, this S dot is the entropy production rate, and you can see that this is basically the Carnot. This is Carnot, and we have some plus this thing. So in this paper, the authors have shown that they are beating the Carnot efficiency for some topological age state thing. So we are looking for whether we are also getting some kind of this thing, but we are not, because this TS dot, if you calculate, this becomes this, and the second portion is, this is a complete square. So this is always positive, and this is related to the thermal conductance. This is always positive. And this is when you combine these two, this is actually the power, and the power in our case is positive. So this thing is always positive. So we have some negative value here and here. So we are not beating Carnot for sure, but we are getting some improved efficiencies because of the application of the spin orbit coupling. So if you add all this and calculate these integrals, you can see that it's better than the without spin orbit coupling case. So lastly, I would like to mention some of the results of our ongoing work. This is basically on the short noise, and we are looking whether we can have some effect on the short noise scenario as well. So what is that? So noise, we all know that it's actually some kind of fluctuations one can have on top of the average current. So this is the time average current, and you can have some fluctuation above and below this. So this fluctuation can appear because of the thermal fluctuations, and also it can appear for the discrete nature of the electrons. So by discrete nature, I mean that if you, as we are placing the quantum dot in between, so electrons need to choose whether they go and transmit or they reflect back. So because of this choice, it is called the partitioning of the short noise, and because of that, this short noise actually appear because of this choice of the electron. So I don't have much to say in this case, but what we do is basically we calculate the current correlation, and this is the noise power spectra, and this is the current correlation, and if you calculate that, you can have this kind of two terms. So the first term you can see that this is appearing due to the thermal fluctuations. So because once you have the t equal to 0 case, your this f into 1 minus f goes to 0, because you know f is a step function, and because of that, if you take t equal to 0, this goes to 0. So this is actually what the thermal fluctuation part, and this part is basically because of the partitioning I just mentioned. So here it is 0 when you have no biasing. So what we get, this is without spin orbit coupling case. So with spin orbit coupling case, we take FL is equal to FR equal to some common Fermi function, and for t equal to 0. So what we should expect? We should expect nothing, because in the previous slide we have, if we have t equal to 0, this term goes away, and if you have FL equal to FR, this term goes away. So we can expect nothing, but we are getting something. We are getting this huge expression, and these are t square minus t kind of a thing. So we are still analyzing this. So this is completely driven by spin orbit coupling. So we can call it some photo-induced noise. So we are still working on it, and so these are the results that I would like to mention. That I had shown you the cross correlation part. So you can have the cross correlation and autocorrelation, and these are for the spin without time dependent driving. These actually holds this SLL is equal to minus of SLR, and in fact what we are getting, that even if you have the time dependence, you still have this relation that is holding. And also we have some short noise in presence of 0 bias condition and 0 temperature condition. So okay, so this is the summary of my talk, and okay, so thank you.
Thanks, Devoshri, for taking time.
Okay.
You finished 1 minute early.
Okay.
So we can take one question, very quick one.
How does the breaking of that mirror symmetry, that DR not equal to DR,
Yes.
is that helping in breaking the time universal symmetry and the SOC?
No, that is different, yes.
So what is that doing, that mirror symmetry?
That mirror symmetry is actually deciding whether you have some DC particle current in the system or not, because when DL is equal to DR, you don't have any DC current in the system. So that is only because of that. So where we place this quantum dot, that is the main thing. So that has nothing to do with this time universal symmetry. Yeah.